Hey Data Geeks, welcome back to my channel Data Structure, your go-to channel for all things data. Let me welcome you to my new series called the Back to Basics series where I will be explaining the basic concepts of data science and data analytics, starting with the most important topic, statistics. Today, we are going to dive into the fascinating world of statistics. Anyone related to the field of data knows the importance of statistics. Whether you are a student, a professional, or just curious about how data shapes our world, this video is for you. So let's get started. And if you enjoy the content, don't forget to like, comment, and subscribe. If you have any questions regarding any topic or want any kind of clarification for any of the topics I have explained, please don't forget to mention it in the comment and I will get back to you. So let's start with the first, what is statistics? To understand the importance of statistics, we should first understand what is statistics. Well, statistics is a branch of mathematics that deals with collecting, analyzing, interpreting, and presenting data. It's all about making sense of numbers and finding patterns in data to make informed decisions. Whether you are looking at sports scores, election polls, or your grades, statistics will help you understand what's going on and predict future outcomes. Let's understand this by a basic example. Imagine you are a teacher and you want to understand the performance of your students in the recent math test. You decide to use statistics to analyze the test scores. You found out the average score of the students, then you find out what percentage of students have scored below the average score and decide to frame your teaching material focused on the students who have scored less than the average score. This way, you have used statistics to find out the optimal teaching method for your students. Is statistic a new concept? Well, no. Statistics has its root in ancient times. Early civilizations like the Egyptians, the Babylonians used basic counting and record keeping for agriculture and taxation. Birth of modern statistics took place in the 17th century where statisticians like John Brown, known as the father of demography, analyzed mortality data in London. In the 19th century, Carl Friedrich Gauss developed the method of least squares, a key technique in regression analysis. The 20th century brought significant advances in the field of statistics. Pioneers like Ronald Fisher and Carl Pearson developed foundational theories in hypothesis testing and correlation. The advent of computers revolutionized statistics, enabling complex data analysis, which brings us finally to the digital age. Today, statistics is integral to the digital age. Big data and machine learning rely heavily on statistical methods to turn vast amounts of data into actionable insights, driving innovations across industry. Let's look at some of the key concepts of statistics, starting with the data collection. Data collection is the process of gathering information to analyze and make decisions. It involves various methods to ensure we get accurate and relevant data. Collecting accurate data is essential because it forms the foundation of your analysis. Good data collection leads to reliable insights, while poor data collection can result in misleading conclusions. There are two main types of data collection: primary method of data collection and the secondary method of data collection. Well, primary data collection involves collecting data directly from the source where you collect data firsthand. Example includes surveys, interviews, and experiments. And secondary data collection uses existing data collected by others where you use existing data. Example include using reports, historical data, and online databases. Let's look at an example. Let's say you are a teacher who wants to know how students feel about a new teaching method. How you can collect the data. Primary data collection: you could create a survey and ask your students to fill it out, answering questions about their experience with the new method. Or you can collect data secondary by looking at existing research studies or reports on similar teaching methods to see how students in other schools felt about it. Then comes the sampling method. Sampling is the process of selecting a subset of individuals from a population to estimate characteristics of the whole population. The sampling methods help us choose a representative group from a large population, ensuring our data is manageable and meaningful. Imagine you want to find out the average height of students in a school. Measuring every student is impractical, so you decide to use a sampling method. Here are some common sampling methods, starting with simple random sampling. As the name says, it's simple and it's random. It means that the sample is selected from the population randomly so as every member of the population has an equal chance of being selected. Example, drawing names out of a hat to choose participants for a survey. Let's look at the systematic sampling. In systematic sampling, every nth member of the population is selected after a random starting point. First, you select a random starting point and start selecting every nth member of the population on the list. Example, surveying every 10th population on a list. The stratified sampling. The population is divided into subgroups or strata based on a characteristic, and random samples are taken from each stratum. Example, dividing a school into grades and randomly selecting students from each grade. Then comes the clustering sampling. The population is divided into clusters and few clusters are randomly selected. All members of the chosen cluster are then surveyed. For example, selecting a few classrooms in a school and surveying all students in those classrooms. And finally, the convenience sampling. As the name suggests, it is a sampling method that is done on your convenience. Well, samples are taken from a group that is easy to access or contact. For example, surveying friends or colleagues because they are readily available. Let's move on and take a look at the data types. Now, in statistics, data can be classified into different types based on their characteristics. Understanding these data types is crucial for selecting the appropriate statistical methods for analysis. So here are the main data types. The quantitative. We have quantitative data which includes numbers, represents numerical values and can be measured or counted, can be either discrete or continuous data. Now, discrete data are countable items like the number of students in a class, while continuous data are measurable quantities like height or weight. Now, on the other hand, qualitative data includes non numerical informations like colors or names. This can be nominal, which means no specific order like eye color, blue, green, brown, or ordinal, categories with a meaningful order, but no fixed intervals between them like movie ratings, poor, fair, good, excellent, etc. Now, importance of data types in statistics we have to understand, because by categorizing your data correctly you can choose the right statistical method to analyze it and draw meaningful conclusions. Now how can we do con- now how can we draw meaningful conclusions? Here where descriptive and inferential statistics come into play. Let's understand what descriptive and inferential statistic is. Descriptive statistics involves summarizing and organizing data so that it can be easily understood. This type of statistics is used to describe the basic features of the data in a study. Imagine you have the test scores of a class. Descriptive statistics can be used to summarize and organize the data in the following way. By finding out the mean. The mean gives us the average, which is essentially the sum of all values divided by the number of values. Following our example, if we add all the test scores of our class and divide it by the number of students, we will get the average score. Whereas the median shows only the middle value. when data values are ordered from least to greatest. So consider the test scores. We have 9 test scores. Then we have to find the median by adding the middle two scores and dividing it by 2. The mode, on the other hand, tells us the most frequent values, the values that occur most frequently in the data set, and the range is the measure of dispersion. The range is the difference between the highest value and the lowest value. Now let's understand variance and standard deviation in a little bit of detail. What is a variance? The variance is a measure of dispersion. Variance measures the average squared deviation of each data point from the mean. You can see on the screen the formula for variance is sum of x minus mu whole squared divided by n, where x stands for each individual data points, mu stands for the mean of the data, and n is the number of data points. On the other hand, standard deviation is used to measure the spread of our data. Standard deviation is the square root of the variance. It provides a measure of the average distance from the mean. So you can see the formula for standard deviation is square root of variance. Let's move ahead and look into the inferential statistics. Now, inferential statistics helps us make conclusions on predictions about a larger group known as population based on a smaller group known as sample. Imagine you have a big jar of candies and you want to know the average number of red candies in the jar without counting every single candy. Instead, you take a handful of candies as a sample and use that information to make an educated guess about the entire jar. That's what inferential statistics is all about. Now let's look at some of the key concept of inferential statistics, starting with population and sample. The entire the entire group you are interested in, or the entire group for which you are drawing inference for, in this case the candies in the jar. Sample is a smaller group selected from the population which helps us draw inference for the population. In this case the handful of candies. Now sampling, as we have seen earlier, can be done through various sampling methods known as simple random sampling, systematic sampling, stratified sampling, cluster sampling, and convenience sampling. As we have already looked into the sampling methods, let's move on and look into the central limit theorem. The central limit theorem, which helps us understand the distribution of sample means. The central limit theorem is a fundamental concept in statistics that describes how the distribution of sample means approaches a normal distribution, regardless of the shape of the population distribution, as the sample size becomes large. The central limit theorem tells us that distribution of sample means will tend to be normal given a sufficiently large sample size, regardless of the population's distribution shape. This is crucial because it enables to use the normal probability method in many practical situations, even when the population distribution is unknown. Now let's look at the hypothesis testing, which is a very important concept in the field of statistics. Now, hypothesis testing is a method to test if a certain claim about a population is true or not. There are null hypothesis and the alternate hypothesis. Null hypothesis is the default assumption, that is, there is no difference between two groups. For example, let's suppose you want to test if the average height is 5.6 feet. The null hypothesis is that the average height is 5.6 feet. On the other hand, the alternate hypothesis is the opposite of the null, that is, there is a difference. So, for the assumption, the alternate hypothesis will be the average height is not 5.6 feet. Now, hypothesis testing helps us determine if our findings are statistically significant. We start with a null hypothesis and an alternate hypothesis. When we then calculate the p-value to decide whether to accept or reject the null hypothesis and do some test like the z-test, the t-test, chi-square and ANOVA. Before we move on to our common tests of hypothesis, let's learn about the type 1 and type 2 error and the p-value. Well, type 1 error is rejecting the null hypothesis when it's true, and type 2 error is failing to reject the null hypothesis when it is false. Type 1 error or the false positive, like thinking a medicine works when it actually doesn't. For example, let's suppose that you are a farmer and you are using a new type of fertilizer for your crops, and you conduct a test to find out that whether the new fertilizer works or not. And type 1 error in this case would be concluding that the new fertilizer actually works when it in fact doesn't. And type 2 error is known as false negative, like when thinking a medicine does not work and when it actually does. So, if we look at it from our example of a farmer, we can type 2 error would be concluding that the new fertilizer does not work when it actually does. So, what is p-value? The probability of obtaining the observed result or more extreme if the null hypothesis is true. In simple language, if this is low, it means your results are unlikely to have happened by chance. So, you can reject the null hypothesis. If the probability of getting an observed increase in yield by chance is very low, we reject the null hypothesis. So now that we have used some tough words, let's understand it in a simple word. The p-value is a measure used in statistical hypothesis testing to determine the strength of the evidence against the null hypothesis. It represents the probability of obtaining test results at least as extreme as the observed results, assuming that the null hypothesis is true. Small p-value gives us a strong evidence against the null hypothesis leading to its rejection, whereas large p-value gives us a weak evidence against the null hypothesis, failing to reject it. Now let's look at some of the common hypothesis testing. Hypothesis testing is a statistical method used to make decisions about a population based on a sample data. There are there are tests to evaluate our hypothesis testing, and some common hypothesis tests are the z-test, t-test, chi-square test, and ANOVA. Let's look at it one by one. The z-test, used to determine whether there is a significant difference between the sample mean and the population mean when the population variance is known and the sample size is large, greater than 30. So the definition of z-test give us the formula also, which is mean of x by minus mu divided by standard deviation over square root of n, where x bar is the sample mean, mu is the population mean, standard deviation is known, and n is the sample size. Let's move on to the t-test. T-test is used to determine whether there is a significant difference between the sample mean and the population mean when the population variance is unknown and or the sample size is small. So the formula for t-test is x bar minus mu by n, square root of n. Now comes the chi-square test. Chi-square test is used to determine whether there is a significant association between categorical values. The formula for chi-square is given, and finally comes the ANOVA. Now, or analysis of variance. Now, ANOVA is used to determine whether there is a significant difference between the means of three or more groups. So, basically, the ANOVA represents the variance between the groups and the variance within the group. Each of these tests help determine whether observed data significantly deviate from what we would expect under the null hypothesis. Let's move on to the regression analysis. Now, regression analysis is a very powerful statistical method used to examine the relationship between two or more variables. It's widely used in data science for predicting, forecasting, and determining causal relationships. Here are the key types of regression analysis that a data scientist should be familiar with. The simple linear regression. Simple linear regression examines the relationship between two variables, one dependent variable and one independent variable, y and x. Example, predicting house prices based on square footage. The formula for linear regression is given where y denotes the dependent variable, x denotes the independent variable, the beta 0 denotes the intercept, and beta 1 denotes the slope. And finally, the epsilon denotes the error term. Let's move on to the multiple linear regression. Multiple linear regression examines the relationship between one dependent variable and two or more independent variables. Example, predicting house prices based on square footage, number of bedrooms, and age of house. The formula for multiple linear regression is given where y denotes the dependent variable, x1, x2, and xn denotes the independent variable, beta 0 denotes the intercept, and beta 1, beta 2, and beta n denotes slope, and epsilon is the error term. Then comes the logistic regression. Logistic regression is used when the dependent variable is categorical, often binary, estimates the probability that a given input point belongs to a certain class. For example, predicting whether a student will pass or fail an exam based on study hours and attendance. The formula for logistic regression is given where P denotes the probability of the event occurring and 1 minus P1 denotes the probability of the event not occurring. There are few more regression types which are a little advanced in nature and I have not mentioned here, which are polynomial regression, which is a form of regression where the relationship between the independent variable and the dependent variable is modeled as the nth degree polynomial. Then there is the ridge regression and lasso regression and elastic net regression, Poisson regression, and quantile regression. If you want to know more about all of these regression, please put a comment in the comment box saying for a new video, and I will try my best to explain this in a separate video. Now let's move on and understand why these regression types matter. So, prediction accuracy. Different regression techniques can improve the accuracy of your predictions based on the nature of the data and the problem. Interpretability. Some regression models, like linear regression, are easier to interpret, which is important for understanding the relationships between variables. Feature selection. Techniques like lasso regression help in identifying the most important features, reducing dimensionality, and improving model performance. Handling different data types. Different regression methods are suited to different types of dependent variable. Example, logistic regression for binary outcomes, Poisson regression for count data. So, after logistic regression, let's look at another key concept known as the confidence interval. Now, confidence interval is a range of values within which the true parameter is expected to fall and with a certain level of confidence, let's say 95%. This gives us a range that we are fairly sure that true value lies within. For example, if we say that we are 95% confident that the average height of students in a class is between 5.5 feet and 6 feet, it means that 95 out of 100 cases, the true average height would be in this range. Confidence intervals necessarily measures the average height of their sample and calculate a range or confidence interval where they believe the true average height of all students falls. Let's consider another example. If we say that we are 95% confident that the average yield of corn is between 80 and 100 bushels per acre, it means that if we repeated this study many times, 95% of the time the true average yield would be within this range. So there you have it. We have covered all the basic concepts that you need to know as a data analytics or data scientist. Now, let's understand briefly what are the applications of statistics in data science. So, the statistics is crucial in data science for exploratory data analysis, making predictions, building predictive models, and decision makings. By applying this statistical method, data scientists can uncover insights and drive business and scientific advancements. Let's look at it in a detailed way. In exploratory data science, using descriptive statistics and visualization techniques to understand the data, looking at your data with graphs and summary statistics to understand what's going on, creating graphs and summaries to understand patterns in crop yields and animal productivity can be an example of exploratory data analysis. Then we use statistics for probability models for predictions. Applying probability distribution to model uncertainties and make predictions, that is using probability to make predictions. For example, weather forecast use past data and probability models to predict rain. Using past weather data to predict future rainfall, helping us plan irrigation. Then we have statistical inference for decision making, using hypothesis testing and confidence intervals to make informed decisions based on data. Making decisions based on data analysis, for instance, a company might use hypothesis testing to decide if a new product is better than the old one, deciding whether to use a new type of seed based on testing a sample and analyzing the result. And then comes the predictive modeling. Building predictive models to forecast outcomes and understand relationships between variables. Creating models that can predict future outcomes. For example, predicting house prices sorry, based on size, location, and other factors. Building models to predict future harvest based on current planting conditions and historical data. So that's a wrap on our introduction to statistics. I hope you enjoyed this video, and if you enjoyed this video, give it a thumbs up and subscribe for more content. Drop your questions in comment below and we'll see you in the next video. Thanks for watching.